Are you able to see the board? We will be studying about the black body spectrum. One more time, we will try to revise it, and then we will see the failures of Weyl and also the failures of Rayleigh genes, and how later on it was the spectral distribution was black body spectral distribution was explained by uh, Planck's. Okay, so see, this was a spectral distribution which we have already studied. This is a graph of the energy distribution, energy density of a black body which is emitted in a cavity. Okay, imagine a cubical cavity in which uh, of a particular distance or length A. Okay, and then imagine that black bodies are emitted within this region. Okay, it need not be that the black body travels along x direction. It may travel along the y direction, or it can travel along the z direction with a particular wavelength. Okay, so Wayne tried to explain. I'm just summarizing all the classes of the previous ones. Okay, Wayne explained that there is a displacement of the spectral distribution with time. Okay, that law we have already studied as Wayne's displacement law. Okay, with the change in the or increase in the temperature, the wavelength is getting shifted from lambda 1 to lambda 2, lambda 3, and lambda 4. Okay, there is a shift. So, which he called it as a Wayne's displacement law. Okay, later on, and this Wayne's displacement law was able to explain the region where the wavelength is less. Okay, this is a lower wavelength region, and this is the higher wavelength region. Okay, some books explains with respect to the frequency. Okay, so I'm not going to speak about the frequency. One term, let us take it into account, the wavelength portion. Okay, otherwise it will confuse you. So in the lower wavelength region, you will find that the wavelength is shifting towards the lower side with temperature, which Wayne explained it as Wayne's displacement law. Okay, Wayne's law could hold good in the lower wavelength region. This portion, this is a lower wavelength region. Okay, this is a lower wavelength region, and this is a higher wavelength region. Okay, so Wayne's explanation was holding good in this lower region. Okay, he said that energy is getting absorbed. Okay, when a body is heated to a particular temperature, okay, the molecules there try to absorb the energy, and they will try to vibrate, they will try to move, okay, in the waveform. Okay, that is what they explained. And they said that the energy goes on getting absorbed. There is an process of absorption on this region. Okay, in this particular region, you will find that the energy is getting absorbed, goes on, absorption goes on, goes on, goes on, and therefore, okay, the spectrum reaches a peak. And once the maximum absorption is over, okay, so I can say this is a region of absorption of the energy in a black body. Okay, the energy is getting absorbed by the body, and therefore it goes on increasing, and once it reaches its peak, okay, in the in the in this wavelength region, the the black body will start emitting radiation. Okay, so that emission, okay, when the black body is giving away the energy in the form of heat, it radiates. Okay, the radiation starts taking place in this region, and therefore there will be a down, the curves goes on decreasing in this side. Okay, so this two portion was well explained by later on by Planck. Okay, but in the higher wavelength region, Wayne's explanation could not hold good. Okay, so therefore Rayleigh and Jean, they came up with their own law. Okay, they that derivation which I have explained in the previous video, which I have put it today. Okay, you can go through it by systematically with the handouts. I have sent it already like this. Okay, please go through it. This handouts, black body radiation, I've already sent it to you. Okay, please go through this handout slowly, and then with the video you can try to understand. Okay, now Rayleigh Jean's law could hold good in this higher wavelength region. Okay, so I can write Wayne's law holds good in the lower wavelength region. Okay, whereas in this, okay, in this region I can say, okay, in this region it was Wayne's explanation was good in this region. Okay, in this region of the spectrum, in the higher wavelength, okay, in the higher wavelength, Rayleigh and Jean's explanation hold good. Okay. Okay. But the entire spectrum could not be explained. Okay. In the video which I have already given, they have derived a formula. Okay. You will come up with the formula of, let me just. Okay. Rayleigh and Jean's law, I will just try to explain it in short. Okay. In the video, it's already explained, but still I will explain. They try to bifurcate. See, the wavelength, the black body is traveling through all XY direction, and they try to calculate the frequency, the number of frequency within a particular volume. Okay, how did they do it? They try to take the number of modes. Okay, they try to take the number of modes. Okay, whatever is the modes. Okay, the number of in a particular, see, to calculate how much number of waves are traveling in a particular volume. Okay, you need to know, you have to divide that particular volume into a small portion called modes. Okay, and then try to calculate how many number of waves are crossing this in a particular with a particular frequency of nu. Okay, with a particular frequency of nu, and with in between. Okay, they try to take two rings. Okay, and they try to find the volume occupied between this region of nu and nu plus d nu within this spherical rings. Okay, within this spherical rings, they try to calculate how much is a frequency, how many number of modes of vibrations are traveling within these two regions. Okay, in this shaded region, and then they divide it by 8, because this chosen portion is 1/8 of the entire spherical region. Okay, so they try to calculate the number of modes. Okay, number of modes of vibration, the number of modes of vibration passing through the a small volume, a spherical volume. Okay, and then they multiplied that particular number of modes into the energy of the wave. Okay, this energy of the wave, okay, Rayleigh and Jean, they took it as directly K into BT. Okay, K into the Boltzmann constant. Okay, so the number of frequency, even later on you will find that the number of modes of vibration, this was the one which was taken up by Jeans. Rayleigh and Jean, they tried. Okay, Rayleigh and Jean, they tried to use this very concept of finding the number of modes of vibration within the region of frequency nu and nu plus d nu. Okay, and they multiplied with the energy of the wave. Okay, or I can say energy density of the wave. Okay, so you will get 8 pi, okay, a cube, okay, by c cube nu square. This was a formula which I derived, and I've shown it in the Rayleigh Jeans video. Okay, you have to go through it today fully, and this was the one they came up with. Okay, and they multiplied with the energy, isn't it, as directly kT. Okay, K into T, K is a Boltzmann constant, K is a temperature. And later on, okay, so here you will find that E is proportional to nu square. Okay, you will find most of the book deals with the frequency. Energy is proportional to nu square, or if you take it nu as with respect to the wavelength, nu is proportional to inversely proportional to lambda square. Okay, so this derivation I derived it in Rayleigh-Jeans for you. You have to go through it. Okay, now in this we can see that energy is proportional to the wave square of the wavelength, or energy is inversely proportional to the square of the wavelength. Okay, so if this is the case, then the spectral distribution will show a pattern like this, which I already discussed. Okay, see here, this was a spectrum, isn't it? E versus wavelength. Okay, square and then inverse of the square. Okay, they it was said that, okay, when the wavelength in the lower wavelength, okay, what happens is, according to Rayleigh and Jean, the energy goes on increasing like this. In the lower wavelength, it goes on reaching. Okay, it is because square of the wavelength. Okay, 1 by square of the wavelength, isn't it? When you take the relation between the energy and E versus 1 by lambda square, it goes like at the lower wavelength. Okay, since E is inversely proportional to 1 by lambda square. Okay, it's a square, you have to take it. So in the lower wavelength, the energy has to be very high. Okay, energy is very high at lower wavelength, region. Okay, try to understand this concept. This is very, very important. If you miss to take up this concept in your mind, you will be confused. Okay, you cannot understand what is the ultraviolet catastrophe. Okay, so energy, if the wavelength is in the lower wavelength, energy wavelength less means energy is high. Okay, so in the lower wavelength, the energy should be very high. That means this spectrum will go higher and higher and higher, and it will go to infinity in the, this is a visible region, and it will go in the invisible, in the ultraviolet region. This is UV region, this is a visible region, this is an infrared, isn't it? So there will be an increase in this spectral distribution, and that will reach to infinity at the ultraviolet region. That they called it as ultraviolet catastrophe. Okay, and they said that it's not possible. Okay, so therefore Rayleigh and Jean's explanation on this spectral distribution side was good. Okay, they could explain this half of the path. This up to this half of the path, Rayleigh and Jean's law holds good in this spectral distribution. There was no problem. But when they tried to explain the lower wavelength region, their result was not in accordance to the spectral distribution, because their result was that this graph should go on increasing. All these graphs should go on increasing on one side. It is not coming down. According to their thing, it is going to infinity, rather than it should come down as seen in the spectrum. Okay, that means they were able to explain this spectral distribution in the higher wavelength. This is a higher wavelength region. This is a higher wavelength region. Okay, their explanation was good and hold good to explain the higher wavelength distribution, whereas they could not explain the spectral distribution in the lower wavelength. So Rayleigh and Jean's failure was that their explanation could not hold properly to explain in this lower wavelength region. Okay, whereas Wayne could explain in the lower frequency or lower wavelength region, but they could not explain why the spectrum is going down after reaching a peak. Okay, so these two scientists, Rayleigh and Jean, they are actually another two pair of scientists. Okay, so their explanation was that they could explain only one part of the spectrum. Wayne could explain the lower wavelength spectral region, whereas Rayleigh together with Jean, they tried to explain the spectral distribution in the higher wavelength. but there was no one to give a proper explanation for both. And there was a long time, there was a silent, no one came up to give a proper explanation why it is happening. This controversy was going on almost for more than a half a century. Okay, so later on it was Max Planck who came up with a proper explanation, and he gave an explanation saying that his results of quantum hypothesis, okay, could give an explanation for the lower wavelength as well as higher wavelength. He could give a proper explanation for this entire spectrum. Okay, so now I hope you have understood the failure of Weins and the Rayleigh, and we are now going to move on to the quantum hypothesis. Okay, so the changes that Max Planck made it in his assumption was that, okay, so in the black body spectrum, it was always taken that the black body that was emitted within this black body cavity is traveling in the form of waves, isn't it? It is traveling in the form of waves like this. Okay, it can be along, not only along x direction, it can be along y, it can be along z direction. Okay, or if it is in between x and y, there is an angle, cos angle involved in this. Okay, so this concept was changed by Planck. He said this waves are not traveling in continuously, but they are traveling in a form of quantas, a short discrete packets of energy. Here it is said that the energy is transferred in the form of wave continuously. That was a concept that was taken up by the previous scientists like Wien and Rayleigh and Jean. But Max Planck's hypothesis was that the energy of the wave, okay, the wave or the energy density, okay, is traveling in the form of packets of energy. Okay, packets of energy means, he said that no more it is traveling in this continuous wave pattern, the energy, but the wave patterns are now discrete in the sense it is now like a packet, broken, but okay, like a discrete packets of energy, the waves are traveling. The waves with a particular energy are not traveling continuously like this. Try to understand. Okay, but the waves are discrete, means separate, but are continuous, but they are separated. Okay, that discrete packets of energy concept was introduced by Max Planck. Okay, so when the assumption that was taken up by the Wien or Rayleigh and Jean is being now taken, that the energy is traveling in the form of packets of energy like this. Okay, small packets of energy called as quanta. Okay, this he called it as quanta, or I can say packets of energy. Okay, for example, I can say, see, you have a chow mein packet. You will find that chow meins are just wrapped, like you must have seen this Hakka noodles and all these things, right? They are in the waveform, continuous. Okay, so if you entirely boil it and try to make chow mein, one will go this many long and it has to go into the mouth. Okay, such a big long waves of the noodle chow mein has to go into your mouth, right? But it will be easy. As a mother, what I'll do, I'll crush it. Okay, I'll crush it and then I boil it so that it will boil quickly and then easy to chew also. No? It won't be falling down your mouth. Okay, children's of course like it, but we parents doesn't like it, right? So it's easy for us to take it in a spoon, okay, and eat it because it won't be very long and falling down from your mouth, right? The same way, here also the assumption is it is not the continuous waveform, but it is like a broken chow mein packets. Okay, the chow mein noodles. Okay, imagine that if you broke the chow mein once, okay, you will find that small bits and things, right? So like the bits, the energy is traveling. This is what was proposed by Max Planck as a hypothesis, and he said that the energy, in a mathematical form, he put it as E is equal to h nu. Okay, so earlier it was just E is equal to frequency. Directly the relation was what? E is equal to nu, and the relation was E is proportional to nu square. Okay, of course it's related to E is proportional to the frequency. Okay, here he said it's just not the square of the frequency, but it is associated with a term called h. Okay, associated with a constant, which he called it as a later on his name itself, that concept, the constant was named as Planck's constant. So energy is proportional to the frequency, but associated with a constant, which he called it as Planck's constant. Okay, you know the value is 6.623 into 10 to the power of minus 34, right? And the unit is there. Okay, so this is what was proposed by Max Planck to make things easy. He said that their energy is not continuously traveling, but it is traveling in the form of packets of waves with a particular frequency, which is associated with a constant value, say some numbers, and that value is called as Planck's constant, which was named after him as Planck. Okay, constant. Okay, so now I will just give you the outline of what Max Planck has tried to explain. Okay, comparing with the Rayleigh-Jeans law. Okay, in the once again, let's come to the Rayleigh-Jeans law. Okay, so here he has written E is equal to 8 pi square a square by c cube into nu. Okay, E is proportional to, these are all constant. A, you know, the length of the cube, isn't it, of the black body, c being the velocity of the light. Okay, these are all constant, into E is proportional to nu in the previous case, nu square. Okay, now Max Planck has replaced this entire value of these things by E is equal to h nu. Okay, and then of course these constants will come because we are going to consider again a cubical box and things like that, so all these things will come. Okay, and then as I said, this was a number of modes proposed by, this was a number of modes, right, into the energy. Okay, what was the value of energy that was given by Max Planck? It was nothing but K into T. Directly they have taken it as, by the equipartition law of energy, they have taken the potential energy as half kT and the kinetic energy as half kT, and together it is 1 kT. Okay, but Max Planck has replaced this equation. This will come as the same. Okay, we are going to derive this again. It's again going to be a big derivation. Okay, so E is going to be having the same value like this. Okay, we are going to similarly derive half of the thing like Rayleigh-Jeans in this Planck's quantum hypothesis also. You will get a similar equation like this. But the KT value was modified. Here alone he made changes. Okay, his explanation was that the energy is not KT, but he gave another alternative value for this. Okay, so this value is going to be, I will give you the value, wait 1 minute, and it is going to be exponential of the thing. We are going to derive this, of course. Okay, we are going to derive this derivation in the next class, next video I will try to put it. Okay, so his derivation will come up like this, 8 pi, the last one. Okay, this is the last value of Planck's hypothesis which we are going to derive. Okay, just the comparison I'm making it. Okay, to the lambda pi. Okay, 8 pi h, here it will come as nu cube by c cube, and 1 divided by e to the power of h nu by kt minus 1 d nu. Okay, this term is going to change, and with a slight changes in this one, not much. Okay, with Planck's. Okay, I'm comparing this. This was the equation of Rayleigh and Jean. Okay, here the energy value was taken as directly as kT, but here it is taken to the power of E raised to the power of h nu. H nu, you know that it is a packet of wave energy that is traveling in a discrete form divided by kT. Here is the main explanation here. E, it is in the varying as the exponential term. kT values now varying in the exponential term of E raised to the power of h nu by kT. Here it is directly kT. Okay, so when he made these changes, okay, this graphical, this E and the relation of the frequency, okay, with the energy, okay, with this equation, he could properly explain both the spectral in the spectral distribution. Okay, Max Planck could explain the reason for the energy to increase and the reason for the energy to get the radiation to be radiated outside. Okay, so he could explain, his explanation was holding good to explain on the both the lower wavelength spectrum. Okay, this is a lower wavelength spectrum and the higher wavelength spectrum. Okay, so Max Planck could make an explanation for why this region in the lower wavelength is getting going on increasing. He called it as absorption phenomena, and this portion of the decrease of the spectral distribution on the higher wavelength, he called it as the radiation phenomena. Okay, so his explanation with this equation was good enough to explain both the lower wavelength and the higher wavelength region in the black body spectrum. Okay, so this derivation we have to do it again. Okay, we will do it and we will come up to this equation, but ultimately the conclusion part I have taken it from the Max Planck, and I have compared it with the Rayleigh-Jean. Okay, so with these few ideas, I hope you will be able to try to go through the Planck's hypothesis. I will send the notes also, and I will also try to take this derivation in the next video and try to upload. Okay, we will see if we can have a direct live class in the next one. Okay, maybe by Monday I will try to see it, or by tomorrow. Let me see whatever is possible by tomorrow or day after tomorrow. I will try to derive this, but it may take again 50 or 45 minutes. And okay, so let's see if I can record it, or I can live stream it in YouTube. Okay, whichever is a possible way, we will try to do it. But this is a very important question and important derivation for your examination point of view. So to understand this, you have to go through the Rayleigh-Jean's law. Okay, and in some books, don't get confused. This portion, you will see that the ultraviolet catastrophe is going like this. If it is going this way, that means here it should be wavelength. In some books, instead of wavelength, they'll be explaining frequency. Okay, if it is with the frequency, energy versus frequency, then this ultraviolet catastrophe will not go like this, it will go this way. Okay, frequency and wavelength, they are inversely proportional. So this graphical representation, if it goes through this, don't get confused. Here you have to check, it may not be with wavelength, it may be with the frequency. When you see the graph, try to understand it, try to see what are the terms that have been explained here. Okay, some books explains with respect to wavelength, some books explain with respect to frequency. I always go for one thing, so I will go with the explanation of the wavelength part. Okay, so I will try to conclude this class. It's just an explanation class with respect to the Rayleigh-Jean and the introductory class of the Planck's. Okay, hope you have understood it. Let's continue in the next class, the big derivation. Okay, thank you and have a nice day. Okay, see you all.